This code is a MM1 queuing system was simulated and a graph depicting the relationship between throughput and load was plotted. Here is the simulation during is set to 200 steps. Multiple different laws are used to observe the system performance. And class simulation uh, re, re, represents an instance of a queuing system that caps a load. Here is store events using the list heap, and here is server busy. Whether the server is processing customers and uh, and here is the schedule arrivals. When initializing, arrange the first arrival event first. According to according to the person process, the time of the next arrival event is randomly generated, and the departure and the scheduled departure. According to arrange the departure events for the compilation of the servers. And here is the main function. Arrange it at each step, retrieve the earliest current event, and update the clock. If the event type is arrival or departure, call the corresponding process function. And handle arrival. The number of arriving customers has increased. Arrange the next arrival event if the server is idle. Arrange the leave immediately, otherwise end the queue. And is handle departure. If the queue is not empty, continue to server severe the next customer in the queue. Otherwise, the server become idle. Uh, through throughout throughput rate equal number of completed servers divide number of arrivals. The average waiting time equal the total waiting time of all waiting customers divide the number of waiting customers. For each load value, create a new simulation and run 200 events. Record the throughput rate each time. When the arrival rate is less than the service rate, the system can handle the arriving customers quickly, and the throughput rate is relatively high. When the arrival rate approaches or exceeds the service rate, the system becomes congested, the waiting queue grows, and the throughput rate decreases. We run the first coding MM1, and the chart indicates that as the load increases, the processing efficiency of the system gradually decreases. Excessive load can cause the system to be unable to handle tasks effectively, resulting in queuing and congestion. And this is the second code, and it's a simple Python script to how to generate the random number using the exponential distribution. it utilizes the random exploratory methods. It's a standard library used for generating random numbers. Make the random number consistent each time is to run the testing and the debugging. If no seeds are set, the number generated each time will be different. The second, the cancel output test indicating that the data to be printed next the expansion process, and it cycle 10 times. Generate a random variable that follows an expansional distribution with a rate lambda equal 10. Format the output as a 4-dimensional places. And we run the coding to test the explanation. The distribution is skewed to the right with many values clustered around smaller numbers and fewer larger values. This is a characteristic of the explanation distribution. And then we run. And this is the third code. The MMEQ system was simulated and access lasted on the varying lots for the following throughput, average delay, server utilization. Uh, Here is initialize the system state and parameters called schedule event to schedule the first arrival event. The default server is rate is 18. Is 18. Here is return. Here is generated a return time that follows an expansional distribution. This is data. This is using a main heap to save the event list or sort it automatically by the time of event occurrence. Pop up the event with the earliest time each time and handle it. Event type arrival equal 1 co-handle arrival, departure equal 2 co-handle departure. If the survivor is running the last survivors and it has not been processed yet, count it to total busy time. Add one to the number of arrivals, schedule the next arrival. If the serial is idle, so server immediately and schedule departure, otherwise queue up. Add one to the number that leaves. If the queue is not empty, the next customer is queuing up. Calculate the waiting time, appointment schedule survivors. If the queue is empty, the server become idle. Record the during of this service. Throughput equal number of departures divide the number of arrivals. Average latency equal total waiting time of all waiting users divide number of waiting users utilization rate. equal busy time divided total simulation time. Perform a simulation for each load once and save the results. Throughput approaches 100% when the load is less than the service rate. Average latency increase with the increase of the load congestion. Utilization approaches 100% as the load increases, which may eventually lead to system congestions. The code 3. Throughput decreases with higher load. This is a typical behavior, indicating that the system struggles to handle too many requests. Average delay increases significantly as load grows, showing that the system becomes slower and more congested. Server utilization increases steadily with load and eventually reach 100%, meaning the system is fully utilized, and any further increase in load could likely cause a system breakdown. Three graphs give a clear picture of how the system behaves under different levels of load, showing the trade-off between efficiency and congestion.
Let's continue with the first code. This code generates 1000 random numbers between 0 and 1 and visualizes them using a scatter plot. Specifically, the program first sets a fixed random seed, this one, to ensure that the same random number sequence is generated each time the program runs. This is useful for debugging or scanners where consistent results are required. Next, the program uses the random function to generate random numbers. Each call to this function generates a floating point number between 0 and 1. In the program, 1000 such random numbers are generated and stored in a list called random value. At the same time, an index is assigned to each generated random number and stored in the index list, representing its position in the sequence. During the random number generation process, the program also prints each random number to the console using print. This is formatted to 4 decimal places so the user can see the generated values. Afterward, the program uses the matplotlib library to plot the scatter plot. And with the random value list on the X and the index list on the Y. This means the X represents each generated random number and the Y represents its position in the sequence. In the scatter plot setting, this one is used to plot the points where the parameters alpha equal 0.6 give the point some transparency, and S sets the size, and color sets the color. And grade true at the grid lines to the chart to help observe the distribution. Finally, the program calls show to display this generated chart. Now we run this code. Okay, this chart is our generated chart. So this code, the user not only generates and stores a series of random numbers, but also visually observes their distribution through the scatter plot. Since these random numbers are pseudo-random and remain consistent each time the program runs, the user can analyze whether these random numbers exhibit a uniform distribution or any other pattern through the visualized chart. Okay, next code is we continue with the fifth code. This code generates 1000 pseudo-random numbers using a layer congressional generator and visualize them through a scatter plot. First, the program set a random seed based on the current time in microsecond. And ensuring that each time the program runs, the generated random number sequence will be different and unpredictable. Then the program defines some constants that determine how the random numbers are generated. By using these specific constants, we can create a long and complex sequence of random numbers which enhances their randomness. Next, the program generates random number using the LCG formula. Each number generated depends on the previous one, and the result is normalized to fall between 0 and 1. Ensuring the random numbers are suitable for various applications, the program also prints the first few generated random to make sure the programmer can check these values. Afterward, the program visualizes the random numbers using a scatter plot with the x representing the index of each number and the y representing the value of the random number. This scatter plot allows user to see the distribution of the random numbers and assess whether they appear to be random. Then we run this code, we can get the scatter chart and some few generated values. This is our chart. Additionally, the program lets users customize the number of random numbers to generate and how many values to print, providing flexibility for different needs. Overall, this code effectively demonstrates how to generate pseudo-random numbers using the LCG method and helps users analyze the distribution of these numbers through visualization, making it a useful tool for understanding the random number generation process. Now we continue with the sixth code. This code demonstrates the generation of pseudo-random numbers using a layer congressional generator, like the last code. The core the functionality of the program lies in the LCG function, which generates a sequence of random numbers based on a simple mathematical formula. This formula. This function accepts several parameters, the A, C, and M. AC and M, C and the seed and the count, and variables. So the LCG formula used is this x equal a multiply the x and add the c, then mod m. This formula ensures that each new random number depends on the previous one, creating a sequence of numbers that will predictable appears random. The program begins by setting the initial value to seed, and then it reads to calculate the next number in the sequence using the LCG formula. After calculating each new random number, it appends it to the values list. If the variables flag is set to true, it prints each generated number along with its index for the user's review. And the function returns the list of generated values once our iteration complete. This sequence can be used in various applications that require random values, such as simulations or random data generation, by adjusting the parameters like the multiplier a and increment c and modulus m and seed. The behavior of the random sequence can be controlled. And in practice, for the example, we use these values a equal 2 and c equal 4, m equal 5 and c equal 3, and count equal 99, and the variables is true. We have the example. If we run this code, we can get the value. In summary, this code showcases how to generate a sequence of pseudo-random numbers using the linear congruently generator. It allows flexibility in generating different types of random sequences by modifying the parameters, while also providing the option to monitor the sequence generation process through printed output. So we continue with 7. Wow. Now this code simulates an MM1 queuing system and visualize the throughput performance under different loads. The MM1 model represents a simple queuing system where both the arrival and service time follow exponential distributions. The code is structured to simulate the arrival of packets, their service time and departures, and then calculate and display the system throughput for various arrival rates. It also uses I think it also uses priority queuing to manage events and random number generators to simulate the randomness in arrival and service time. The code begins by importing necessary libraries, including HAP for managing the priority queuing of events, random for generating random numbers, and MATLAB and Matplotlib for plotting the results. The constants arrival and departure represent the type. It's a type of events in the system where the simulation runs for predefined numbers of events. And this code defines an array of different lots. Ranging from 10 to 200 in increments of 10, which will be used to simulate the system's behavior under different conditions. I think it's 200. At the core of the simulation is simulation class, which models the behavior of MM1 Queen. The class has several key methods like the initialization. This sets up the initial conditions of the simulation, including the clock, event queuing, and the system state, and the random number generates for arrival and service time. And this one initialize the first arrival event and add it to the event queue. Then event schedule. Event schedule this function, I think this method pops the next event from the priority queue and processes it depending on whether the event in an arrival or departure. It will call the appropriate method, like the arrival or departure. And random number generates. This tool is generate inter-arrival and generate service method use exponential distribution to generate inter-arrival times and service time, respectively. And arrival event, this function, I think when a packet arrives, if the server is idle, it starts servicing the packet immediately and scheduled departure. If the service is busy, the packet is added to the queue. Then departure event, I think departure event, when a packet departs, it checks if there are any packets waiting in the queue. If there are, the next packet starts service. Otherwise, the survey become idle and results calculation. This function result calculation after processing all events for a given load. This method calculates the throughput defined as the ratio of successfully departed packets to the total packets that arrived and prints the results. And for plotting, after running the simulation for each load, the program visualizes the results. The visualize output function uses matplotlib. plot the throughput as a function of load. It generates a line graphic where the x represents the load and the y represents the throughput, helping to illustrate how the system's performance changes with varying levels of demand. And in the main simulation loop, the program runs the simulation for each load in the defined range. For each load, it creates a new simulation instance, runs the simulation for the specified numbers of events, and records the throughput. Once our simulations are complete, the results are plotted, showing the relationship between load and throughput. If we run this code, we can also get this chart. Overall, this code provides a powerful tool to study the performance of an MM1 cleaning system under different conditions by simulating various arrival rates and visualizing the throughput. It also for a clear understanding of how the system efficiency changes as the load increases, providing valuable insights into cleaning behavior and system optimization. Okay, thank you.
Okay, this code simulated the bus passenger waiting time, assuming the bus arriving randomly, follow an external distribution. You are measure how long people waiting until the next bus, and the goal is to generate data, calculate statistics, and release the PDF and CDF for that data. I will walking you through a Python program that simulated bus waiting times using the external distribution and visual the data with both the probability density function and the column distribution function. The code begins by set parameters for exponential distribution. In our case, the lambda value is set to 1%, which means that the average waiting times for bus in 10 minutes. The program simulated the waiting times for n times equals 10,000 passengers. We also define the range from the x and where the maximum value captures approximately 98% of the distribution, and the minimum value is set to 0. Use the external distribution. The program generates the waiting times for each passenger with the formula. And where lambda is the rate parameter, the generating times are stored in the list waiting times. Then the program calculates the PDF and the CDF. The PDF is calculated using the formula for exponential distribution, where the CDF is driven by integrating the PDF, giving us the probability that the waiting time is less than or equal to given value. The program then calculates the mean and the variance of the distribution. The mean is simply the inverse of lambda, and the variance is the inverse of lambda. These statistics are pinned on the pointer for reference. So from the result. From the result, the picture-1 PDF and the histogram. The first figure contains a histogram of the simulated waiting times, which show how the waiting times are distributed. The histogram is normalized to display the density of waiting times. Overlaying on this history in the histogram in the PDF code, which represents the zerotic exponent distribution, a width Descartes line marking the mean of distribution, and the mean and the variance value are displayed on the paragraph. And from the figure 2 CDF, the second figure is plotted the CDF showing the cumulative probability of waiting times. The CDF starts at 0 and increases towards 1. As the waiting times increase, we present the probability that a passenger waiting less than or equal to a certain times. Again, the mean is marked with a red dashed line, and the mean variance are displayed on the plot. Both figures use multiply lab for visualization, with labels for excellence and green lines to enhance readability. The tonight layout function ensures that the polyps are neatly grounded without overlapping elements. Finally, both figures are displayed together using polyp show, providing a clear and intuitive view of the waiting times distribution. For the second this code simulated and various bus waiting times for two different bus arriving rates using the exponent distribution and plotted both the PDF with histogram and the CDF, and from the Python program that simulate bus waiting times and visualize the result using both the probability designer function and the cumulative distribution function. We simulated this using the exponent distribution, which is often used to model the time between events in a pausing process, such as the waiting time for a bus. The first is parameter and setup. The program uses two different lambda values, one for a high bus rate of 18 bus per minute, and another for a lower rate of 20 bus per minute. The parameter unsample equals 10,000 special the numbers of simulated passenger, and we define the range from the x from 0 to 0.1 minutes as this capture most of the waiting time distribution. The simulation process for each lambda value, the program generated waiting times using inverse transformation sampling. The idea behind the inverse transformation sampling is that we can generate random samples and from any distribution by first generate uniform random values between 0 and 1, and then using the investor of the cumulative distribution function to map that uniform random value to the desired distribution. For external distribution, the formula for this transformation is and where the u is a uniform random value between 0 and 1, and the lambda is the rate parameter. In our case, the number bus per minute. This process simulates the waiting times for 10,000 passengers. And from the result, visualize the result. The program for the result, the first figure contains two subplots. A histogram of the simulated waiting times is plotted for each lambda value. This shows how the simulated waiting times are distributed. The PDF is plotted over the histogram. The PDF curve represents the several exponential distribution for each lambda value. Allow us to compare the simulation to the expanded distribution. The histogram is colored with sky blue for lambda equals 20, and lighting green for lambda equals 18, and the corresponding PDF codes are plotted in red and blue respectively. For the figure 2, the second figure contains two subplots. The cumulative distribution function is plotted for each lambda value. The CDF represents the cumulative probability that a percentage waiting less than or equal to a certain time. It starts at 0 and increases towards 1. As the waiting time increased, the CDF are plotted in purple for lambda equals 20 and orange for lambda equals 18. The histogram and the PDF in figure 1 allows us to compare the simulated data to the several external distribution. As expected, the waiting times for external data pattern with more passengers have shorter waiting times at a high bus rate. The CDF in figure 2 helps us understand the probability that a passenger waiting for a bus with specific times. As the bus rating increases, lambda equals 18. The probability of waiting less than a given time also increased. It means passengers at a high bus rate experience shorter waiting times. Both the PDF and the CDF provide value insight into how the waiting times are distribution under different bus rates. The program using multiplot to increase this value is visualized, and each plot is neatly labels with titles. Additionally, green lines are added to make the chart more readable. for the last this Python code simulating rolling a fair 6-sided die. The calculator and realized PMF and CDF. Basically, statistic means variance standard deviation. So a Python program that simulates rolling a fair 6-sided die, calculates the probability mass function PMF and cumulative distribution function CDF, and realized the result. This type of simulation is a classical example of discrete probability distribution, and it helps us understand how frequently each outcome occurs and how probability was accumulated as we roll the die multiple times. Simulation of roll the die. To begin, we simulated roll the die 100,000 times using the numpy libraries function. This function generation generation random between 1 and 6. Simulated the outcomes, roll a fair die for reproducibility. The random number generator is seeded with number 42, random sims 42, which ensures that the random numbers generation are same each time. The program function. The first 10 rows are printed to give an example of simulation comes from the PMF probability mass function. We calculate the PMF. The PMF tells the probability of each possible outcomes. To calculate it, we use the NP histograms, which count how many times each number from 1 through 6 appears in the simulation, and normalizing it so that the probability sum to 1. This point using a steam point where the x represent the outcomes of the die, and the y shows that the correspond the probability of each outcomes. The cumulative distribution function CDF is then calculated by taking the cumulative sum of the PMF. The CDF represents the probability that the outcome of die roll is less than or equal to give a value. For example, the CDF value for 3 represents the probability that the roll will result in 1, 2, or 3. The CDF is plotted as a line graph. From the result, the CDF plotted as a line graph where the x represent the outcomes to 1 to 6, and the y shows the cumulative probability. From the PMF pollet, the first pollet shows the PMF as the steam pollet, making it easy to visualize the individual probabilities for each die outcomes. From the CDF of rolling a fair die, the CDF pollet, the second pollet shows the CDF, which allows us to see how the probability accumulates as the die roll result in high numbers. Both the pollet using the granular for better readability and are displayed side by side for easy comparison. The pollet help us understand the distribution of the outcomes of the die rolls and how the probability of certain events accumulate. Okay, that's all.